In this lecture, we will discuss about the phenomena electromagnetic induction. So for explaining the phenomena of electromagnetic induction, let us consider a small experimental setup like this. Here we have an iron piece, and over this iron piece a coil is wound, and the two terminals of the coil are connected to a galvanometer, and also there is a bar magnet placed near this coil. This is the experimental setup that we have considered to see the phenomena of electromagnetic induction. Okay, so if we keep this bar magnet stationary, the galvanometer will show null deflection. As long as this magnet is kept stationary, the galvanometer will show null deflection. So we know that when a magnet is kept near this iron piece, some magnetic flux will link with the iron piece and with the coil. But the galvanometer showing null deflection means no current is flowing through the coil. Even though the coil is getting some magnetic flux, no current is flowing through the coil when the bar magnet is kept stationary. Now, if we move the magnet back and forth, we can see the galvanometer is deflecting in opposite direction. That means if we move the magnet towards the coil, the galvanometer will deflect in one particular direction, and if we move the bar magnet away from the coil, the galvanometer will deflect in the opposite direction. So there is a deflection in the galvanometer means there is current flow through the coil. So in order for a current to flow through this coil, there should be an EMF in the coil. So that means when we move this magnet, an EMF is induced in this coil, and this EMF forces current through the coil. That is why the galvanometer is showing some deflection. Okay. So when the magnet moves, what will happen? The flux linking with the coil will change. Okay. When the magnet is kept stationary, a constant amount of flux will link with the coil, and we cannot see any current flowing through the coil under that condition. And when we have moved the magnet, the flux linking with the coil changes, and under this condition an EMF is induced in the coil. This phenomenon is known as electromagnetic induction. That is, when the flux linking with a coil changes or a conductor changes, an EMF will be induced in the coil. This phenomena is known as electromagnetic induction. So here electromagnetic induction is described. Change in magnetic flux linked with a coil induces an EMF in the coil. This phenomenon is known as electromagnetic induction, and the phenomena of electromagnetic induction was discovered by Michael Faraday. Okay. Faraday expressed his findings as two laws. So Faraday stated the phenomena of electromagnetic induction as two laws. There are Faraday's first law as well as Faraday's second law. So this is the statement of Faraday's first law. This is nothing but the definition of the electromagnetic induction phenomena. That is, Faraday's first law states that whenever the magnetic flux linking with a coil changes, an EMF is induced in it. Okay. Whenever the magnetic flux that links with a coil changes, an EMF will be induced in the coil. Okay. So here, according to Faraday's law, an EMF is being induced in the coil. Okay. And there is no information regarding the magnitude of the EMF, and it is given by Faraday's second law. So Faraday's second law gives the magnitude of the induced EMF, and according to the law, the magnitude of induced EMF is equal to the rate of change of flux linkage. The magnitude of EMF being induced in a coil is equal to the rate of change of flux linkage of the coil. Now, what is the term flux linkage? Flux linkage and flux are two different terms. If we have a coil having n number of turns, then flux linkage of the coil is equal to number of turns into phi, where phi is the flux that the coil gets. Phi is the flux associated with the coil. Then flux linkage of the coil is equal to number of turns of the coil into flux that the coil gets. Okay. So according to Faraday's second law, magnitude of induced EMF is equal to rate of change of flux linkage. So rate of change of a quantity means change in the quantity divided by time, that is rate. Okay, rate of change of flux means change of flux linkage divided by time. Okay, so suppose initial flux linkage of the coil is n into phi1. So coil is having n number of turns, and assume initial flux of the coil is phi1, and after a time t seconds the flux of the coil is phi2. So we can write initial flux linkage is equal to n into phi1 and final flux linkage is equal to n into phi2. Okay, so flux changes from phi1 to phi2 in a time interval t. Okay. So according to Faraday's second law, induced EMF is equal to rate of change of flux linkage, that is change in flux linkage divided by time. So here change in flux linkage is final flux linkage minus initial flux linkage, that is n into phi2 minus n into phi1. So that is the change in flux linkage, and in order to get the rate of change we have to divide the change by time. So this change in flux linkage occurs during a time interval t. So we can take n common outside. So n into phi2 minus phi1 divided by t. So this term phi2 minus phi1 divided by t is nothing but the rate of change of flux. Phi2 minus phi1 is the change in flux. Divided by time gives the rate of change of flux. So in differential form we can represent the rate of change of flux as d by dt of phi, d phi by dt. So we can represent this term in differential form like this. Or according to Faraday's second law, the magnitude of induced EMF is equal to n into d phi by dt, where n is the number of turns of the coil and d phi by dt is the rate of change of flux linking with the coil, rate of change of flux of the coil. Now there is another law known as Lenz's law, and this law is used for determining the direction of induced EMF. So we got the magnitude of induced EMF by applying Faraday's second law, and we also need to know in which direction this EMF acts. So Lenz's law will give the direction of induced EMF, and according to Lenz's law, the direction of induced EMF is so as to oppose the cause producing it. Okay, so induced EMF, according to Lenz's law, the EMF induced in a coil will always try to oppose the cause producing it. The induced EMF will always oppose the reason for the production of the EMF. Okay, so it will oppose the cause. So cause is the change in flux. So in order to show that the induced EMF will oppose the cause, we will add a negative sign to the magnitude of induced EMF. So we have to show that the induced EMF is in a direction opposite to the cause producing it. So in order to show that, we will add a negative sign to the magnitude of induced EMF. So we can write the EMF induced in a coil as minus N into d phi by dt.